Hello students, so today we are going to deal with the topic of coherent sources and the interference of waves. So we'll be dealing with this topic and we'll look into the physical aspects in which it manifests. So let's start the part. Hello students, so let's now understand what are the coherent sources. The coherent sources of light are those sources of light which emit light waves having a constant phase difference. So now this is the important word here, that the phase difference is a constant. Have a constant phase difference. Now what do you mean by a constant phase difference? Constant phase difference means if you have two light sources, suppose I denote this first light source by E1, suppose E0 is the magnitude sine omega t. Suppose this is one wave, the second wave is E0 sine omega t plus alpha. Alpha is anything of phi, whatever constant you want to take. Now if you see these two waves, what are the phase? What is the phase of this wave? If I ask you what is the phase of this wave, this is omega t. Whatever is here is the wave that we have discussed. Now what is the phase of this? Let's note this by phi 1. What is the phase of this? This is omega t plus alpha. If I ask you what is the phase difference between these two, then it will be phi 2 minus phi 1, right? It is a alpha. Now if this alpha is a constant, what it means is that these two sources will be coherent. So if alpha is suppose any number, suppose it's pi by 2, anything 0.2, anything, it is a constant. Suppose if the alpha is 2t, where t is time, suppose t is time in seconds, then that means with time this alpha is changing. What that would mean is that phi 2 minus phi 1, this will be changing. Suppose it is 2t, it is changing with time. That means the phase difference is not constant. That means these two sources are not coherent. Now for interference to be produced, that we are going to discuss, we must have a constant phase difference. The phase difference must be constant with respect to time. Now here if you see, how can we get the coherent sources? Coherent sources, they can be produced by two methods. The first is by the division of wavefront. The Young's double slit experiment, this is what we will be discussing in detail. Fresnel's biprism is there, Lloyd's mirror is there. Now what's happening here is, see, suppose you have this wavefront. Wavefront means all of the points that are here have the same phase. Now suppose it is moving like this. Suppose you have a cardboard is there, this is a cardboard, blackened, and it has two slits. One slit is here, another slit is here. These are the two slits that you can see. Now what will happen when this wavefront moving here reaches? What will happen? Only the portion that is exposed to this will be passing here, and exposed to this will be passing here. Now since when this wavefront is exactly here like this, and after some point it will be here exactly on the board, what will happen that this point and this point now have the same phase, because these 2 points are on the wavefront. That means these 2 points have the same phase. So this is called the division of wavefront. Means we had a wavefront, we divided it in such a manner that we got the sources from here. So when the light goes from this point and this point, these are coherent sources. Why? Because they are coming from the same wavefront. Same wavefront means same phase. Same phase means the phase difference is 0. 0 is also a constant. Okay. Second is by division of amplitude. Now how can we get this by division of amplitude? This is through partial reflection or refraction. Like suppose if you have a medium here, this is mu, this is air, light is coming from here. What will happen? Some portion of the light will be reflected, some portion might get refracted. Suppose if you have another medium, you may have this reflection happening here, and then again refraction happening here. So what is happening, that you have the same source. When it reflected, you got a ray, then it moved like this, again it came out, you got a wave. So now here you have a constant phase difference. Constant phase difference. I am not telling here that the phase of this and phase of this is same. Okay, what I am telling is that the phase difference is a constant. It's not changing with respect to time, because you have the one source, single source. Now why I was telling that the phase difference is a constant, that we'll see later, that actually there is a phase difference of pi between these two. But again, that is a constant. We'll be discovering why it is so. But here, since it is coming from a single source, we have constant phase difference. Now these are the two examples. Now suppose this is a prism. The light is coming from here. This is a wavefront. This is a wavefront, means all of this has the same phase. It is coming here. It has the same phase. Then it passes here, and then the light rays come out. Now when the light rays come out, it will be like this, right? We know that in what manner the light will come out. Now when the light has come out like this, how do you draw the wavefront? We draw perpendicular to it. When you draw perpendicular to it, you will find that wavefronts are again like this, same parallel. Okay. Now again, since these are wavefronts, they all have the same phase. Wavefront means it is a locus of points having the same phase. So again, these are coherent sources. This was A, this was B. This A and B were on the same wavefront, so they have the same phase. They cross the prism, but again when they reach here, they again have the same phase, because now they are again on the same wavefront. So we have A and B as a coherent sources. Even after crossing, they have the constant phase difference. Similarly here, it is similar to this. Okay. Now we will see the interference of waves. How do we get the interference of wave? What are the conditions necessary for the interference of wave? What happens when we have the interference of waves? Okay. Now if you see here, these are two waves. One wave is E1, another wave is E2. If you see, the red one is the first wave. This is this. Purple one is the second wave. I draw it here for you. This is E1. Okay. And then you have from here, you have another wave E2. This is what you can see here. Okay. So what we are doing here is that in the interference, it is actually the superposition of waves that you know, that we add these two waves. We are simply adding these two waves. So if you add these two waves, what kind of wave will you get? This will be the superposition, and this is exactly the interference. What is interference of waves? It's simply the superposition of two waves, the addition of two waves. This is called the interference of waves. And we have studied this in the sound, that what exactly is the interference of waves. So it's exactly identical to what we have discussed. What is happening here is that now we are discussing light waves. Now, and in considering the light waves, we consider the electric field of the light waves. We don't consider light as a pressure wave like we considered in the sound. So it's a property that is attached to the light. Since the light consists of electric field and magnetic field, so we are considering that property of the light as the property that is varying here. Okay. Now what is constructive interference theoretically? Now this is what we have to do, is E1 plus E2. Constructive interference will happen when the phase, both are in the same phase. What this means is that, now see, at the same time t equal to 0, here, this wave is here, this is also here. Okay. And at the same time, after some time, if you see here, both are reaching maximum at the same point of time, suppose t. What will happen means, at the time t again, both have reached the same point, so they will add up, right? So it will grow like this. Again, after this, since at time t this happened, so at time 2t this will happen, this will again come to 0. So again at 2t, what is happening is that both of them are at the origin, right? This is also at the origin, this is also at the origin, means both have the 0 displacement. So when you add it, what will happen? It is again 0. Then again it will go like this. So this is the resultant. This you can see, this green one is the resultant, E1 plus E2. This is the reference line that you see. Okay. What is destructive interference? Destructive interference will happen when this is happening. See. You have this is plus, if you have another wave, okay. Now you can see here, it's very easy to see that there is a phase difference between these two, right? There is a phase difference, right? If you see, it is here and it is here. Okay. This is here and this is here. If you can see, this total length is what? This is 2 pi. This total length is 2 pi in terms of phase, right? So if you see this and this, what you can see is that they have a phase difference of pi, right? It's clearly visible here that they have a phase difference of pi, right? Because if you see, this wave is going like this, right? This is going like this. This is a wave. From here to here it's 2 pi. So what happens? Suppose you move from here to here. Now if you see this portion, see the portion after this, once you have moved here, you can see that this portion is exactly identical to this portion. That means after the pi phase, they are exactly same. That's why the phase difference is pi. But actually the figure is this. Okay. So now we see here. Okay. Now we see here this one. What is happening when you add these two? Now when we are adding these two, what we will do is, we will do again the same thing, that we will try to add individually. Now let's add individually. At this point both are at the origin. Okay, so it will be at the origin. Suppose after time t it is here. It is here and this is here. So what is the value? If you see here, this is the position and then this is the position. So suppose this is plus something and this is minus something, right? So what is happening is that if both are equal in the value, what will happen? The net value is 0, right? Again, if you consider this portion, this is positive, this is negative, this. If they have the same value, again 0, this is already 0. If this is same, they are 0. So what you see is this, there is no wave. Now this kind of behavior is the destructive interference. What is the magnitude that is actually happening? It's E1 minus E2. Okay. Vectorially, what interference means is this. Vector E is vector E1 plus vector E2. Right. So if E1 and E2 have the same sign, what will happen? They will add up. If they have the opposite sign, they will be subtracted. So these are the symbols that we use there. Okay. Now let's see the theory of interference of waves. Let's assume that the first wave is A sin omega t, it's varying in this manner. Second wave that you have is B sin omega t plus 5. Now this A is the amplitude of this first wave, B is the amplitude of this second wave, phi is the phase difference. Okay. This phi could be any value. Like we saw in the last example, we had taken pi. Pi means exactly half of the wave has moved ahead. There is that kind of phase difference. Now the waves are moving with the same speed here, and wavelength, frequency, time period, nearly equal amplitude. These are all the assumptions that we are taking. You can take that it's not equal, and we'll see what happens when they are not equal. They are traveling in the same direction. Again, the waves are traveling in the same direction. If the waves are not traveling in the same direction, what happens? We know what happens, right? The standing waves are formed. We have seen all these properties in sound waves. So exactly the same things will be happening here also. So the waves must be traveling in the same direction to get an interference. Now there is a constant phase difference of phi. Between this and this, there is a phase difference of phi. So we'll be looking at here, what are the phase difference? There is a wave here. Suppose it is this. Another wave is here. Suppose maybe it's here like this. So there is a phase difference. Suppose this is phi. Because once you move from here to here, if you can come here, from here you can see that it's exactly the same nature, right? So when this point is this point, they have the same phase difference. But we see that initially the position is this and this, so this is the phase difference phi between these two waves. So it could be any value. It could be pi, it could be pi by 2, anything. Omega is the angular frequency, right? We know omega is angular frequency, 2 pi times nu. Nu is the frequency, 2 pi by time period. You can write it any manner. For this time period, the time taken in going from here to here, this is called the time period t. So the angular frequency omega is 2 pi by t. Okay. E1 and E2 are the instantaneous values of electric displacement. Now since we are considering light, we are actually considering the electrical displacements. So let's see what will happen when we add these two, because that's what the interference is. Now if we add these two, applying the superposition principle, the magnitude will be A sin omega t plus B sin omega t plus phi. We are adding these two. Now how can we write this? Now this B sin omega t plus phi can be written in this manner. It can be written sin C plus sin D. You can write it as, because sin omega t plus phi. You can write it, sorry, this is sin A plus B, so you can write it into sin A into cos B plus cos A into sin B. This is the formula for sin A plus B, where A is this, B is this. So we write it this in this manner, and then you have A sin omega t plus A sin omega t. So this is what this expands into. Now if you take, if you see here, we take first the common as sin omega t. So if you take sin omega t common, what you will have is this. You take sin omega t common, you will have A from this, A plus. Now see where sin omega t is there. Here it is sin omega t. So if we have taken sin omega t, what is the thing that is remaining? It's B cos phi. So it's A plus B cos phi plus, then you take cos omega t. So you, and what remains is B sin phi. So it's B sin phi cos omega t. What we assume is that, let's take A plus B cos phi is A cos theta, where theta is any random value. We assume that this value is cos theta, and this value, this whole thing is, we take as A cos theta, where A is any arbitrary value, and then we take B sin phi as A sin theta. Why we take this? So that we get this kind of form, to look, so that the equation looks simpler. We can always find that value. We can always find A and theta such that these two will satisfy this. Okay. So what we get is that the resultant value is this, A sin omega t plus theta, where A is a constant that you can find out from here, these two equations. Okay. And sin omega t plus theta. Now what is this theta? Theta again you can find it from here. So what you see is that, what will be the resultant field? There was this field plus you had another field. Suppose you had a phase difference like this, some any random value. So you will have a resultant field that will have a different magnitude. Means suppose this has a magnitude of E1, this has a magnitude of E2. When you add, you will have a different magnitude. Suppose it could be larger or smaller, it could be anything. Like we saw, when constructive interference is taking place, magnitude increases. In case of destructive, it decreases. And also it doesn't mean that you will always have a perfectly complete constructive interference. You may have a partial constructive interference. So in that case, the value won't be such high. So here suppose this is A, this is moving. Now the phase difference is theta. Phase difference between this and this is theta. So if this phase could be anywhere. So if this is like this, it won't be like this. It would be something like, suppose this is like this in this nature, and this is theta. Sorry, this is theta. So it could be anything like this. Now, what is the amplitude here? How can you find out the amplitude? If you see from here, what will be A? If you add these two, you can get A, right? See, it's very easy. Square these two and add it. So what you will have is A square, cos square theta plus sin square theta will give you 1, and then you will have this A plus B cos phi square plus B sin phi square. So if you find out, you will have A square plus B square cos square phi, then you have this plus B square sin square phi, and plus 2AB cos phi, that you can see it from here, 2AB cos phi. Now what you see is that from in these two, if you take B square common, you will have cos square phi plus sin square phi, that is 1, and the magnitude is this that we have got here, A square plus B square plus 2AB cos phi. If you see, this was A square, right? So when you take the root, this is the value. And what would be theta? Theta would be B sin phi by A plus B cos phi. It's very easy, you can see here. How to find out theta? Divide this. Divide A sin theta by A cos theta. You will have B sin phi in the numerator, A plus B cos phi in the denominator. So we got the value. This is A, this is tan theta. This is what the resultant electric field will look like when the two waves interfere. Okay. Now having the different values of phi, A and B, you will get the resultant values. E is the resultant displacement of electric field. A is the resultant amplitude, and theta is the resultant phase difference. Now intensity is a quantity that is proportional to the square of the amplitude. we have a quantity called intensity. It is actually proportional to the square of the amplitude. We'll be dealing with intensity in detail later on in our lecture. Now, what will be the condition for constructive interference? What is constructive interference? We have seen what is constructive interference. When both of them are in phase. So when you have the maximum value, in phase means you get the maximum value, both are in the same phase. If you have it like this, then that means these two are in the same phase because they are adding up. When it is here, this is also here. So these two will again add up, it will give you a larger value. So you have a constructive interference. Now see, one thing you must keep in mind, a phase difference of 0, a phase difference of 2 pi or a phase difference of 4 pi makes no difference. Because after 2 pi, it repeats the same nature. So suppose here you have a phase difference of 0. You can tell, okay, this is this. Suppose they have a phase difference of 2 pi. You cannot tell that it had a phase difference of pi or 2 pi, right? If you have simply this, because after 2 pi, if you see this wave will be like this, right? So from 0 to 2 pi is this nature. From 2 pi to 4 pi, it's again the same nature. If you see this and this, they are exactly identical. So a phase difference of 0, 2 pi, 4 pi, they are exactly the same. And a phase difference of pi, 3 pi, 5 pi is again the same. Because it will only mean that you have this from this portion to this portion. Ahead of phase by pi. So you have to keep in mind, this is only I am talking for sinusoidal wave because they repeat after 2 pi. Sinusoidal waves, they have a time period of 2 pi, they repeat after 2 pi. That's why I am telling that it's similar. So when will this value be maximum? It's very easy to see. This will be maximum when this value will be maximum because all are in positive. A square is always positive, B square is always positive. So this will be maximum when cos phi is plus 1 because then it will be A square plus B square plus 2AB. So when cos phi is plus 1, we put the value when the value of cos phi is plus 1. Now we know that cos phi is plus 1 when cos graph is like this. So it is at 0, at 2 pi, at 4 pi it's plus 1. So it's 2n pi where n is an integer. When n is 0, you have 0. N is 1, you have 2 pi. N is 2, you have 4 pi. So you can see at 0 it is maximum plus 1. At 2 pi again its value is plus 1. Again it will be at 4 pi plus 1. So this is what the phase is. Now what is the corresponding part difference? This is phase difference. In terms of phase, angle we are talking. Now what will be in terms of part difference? Now if you see the part difference, now a length of 2 pi in terms of phase is equal to what? Lambda, right? A length of 2 pi is equal to lambda. If you see here, I draw a wave here. What is wavelength? Wavelength is this lambda. And what is the phase? This is 2 pi. So an angle of 2 pi radian is equal to 1 lambda. So that means 1 unit distance is equal to 2 pi by lambda radian, right? 1 unit distance. So delta unit distance will be equal to 2 pi by lambda into delta radian. Similarly the inverse can happen, right? You had this 1 wavelength, 1 meter will be equal to 1 radian will be equal to lambda by 2 pi, and in suppose x radian it will be lambda x by 2 pi. So this is the same thing. So when you have a phase difference of this, if the phase difference is this, what will be the part difference? So part difference you can find is 2 pi by lambda into delta x. So you have delta lambda by 2 pi into 2n pi. When you cancel, you get delta is n lambda. So you can see what exactly is happening, that the part difference has to be integral multiple of lambda. N is again an integer. Means if you have a part difference of 1 wavelength or 2 wavelength or 3 wavelength, wavelength means this portion, you will have a constructive interference. That means because after this it repeats. So even if this whole thing changes to this portion, there is no difference. Means you have a path change of 1 lambda, that doesn't make a difference because it's exactly the same. Similarly, what will happen for destructive interference? We'll have phase difference of 2n plus 1 pi, right? Because in that case, if you see here, cos phi will be minus 1. What will be the minimum value? When this minus, this will be the maximum value in negative. Maximum value in negative of this can be minus 2ab. So that means that will make this minus, cos phi must be minus 1. That happens when phi is equal to pi, 3 pi and 5 pi. You can see it from here. At pi, at 3 pi. So the formula you can write is 2n plus 1 pi, because when n is 0, this is pi, n is 1, this is 3 pi. So this is what is happening here. What is the corresponding part difference? Again similarly you have lambda by 2 pi into 2n plus 1 pi. So we get this. We have simply converted it in terms of wavelength lambda, and we know the 2 pi radian is equal to 1 lambda. So you can convert these two. So let's see an example here. You have two coherent sources emit light waves which superimpose at a point where these can be expressed, this and this, where E1 and E2 are the electric field strength. Find the resultant electric field. Now if this is the electric field E1, okay, the net result, if you remember the net resultant electric field, I can write the magnitude, the values are A square plus B square plus 2AB cos phi, right? Now what is A? This is the amplitude of this is E0. What is B? This is 2E0. What is phi? Phi will be phi 2 minus phi 1, right? So omega t minus pi by 4, this is phi 2, this is phi 1. This whole thing is phase. You have to keep this in mind. So this is this minus omega t plus pi by 4. What you get is minus pi by 2. Right? Put the values here. What you get is root over E0 square plus 2 E0 square plus 2 times A